Okay, let's put some of the idea of exponential functions to use with the particular real world situation. So we have a rabbit population that grows at 7% monthly at this rate. There are 180 rabbits in September. We want to know how many rabbits should be expected by next September. They actually give us a function to use. This is an exponential function, and t represents our time. And we're going to put this in months. So since it's one entire year, we're going to let our months equal to what? 12. Good. So let's fill this equation in and see what we get. Okay, using the given equation, we plug in 12 for 12 months, representing from September to the next September. Get our calculation and we get this, but it wants us to round to the nearest whole number, so we end up with about 415 rabbits. So in 1 year, they increased from 180 to 415. All right, now we're going to talk about functions with a base of e. We have natural base e. And we're going to complete a chart. I'm going to take a few minutes. I want you to pause it and complete this chart, and then we're going to figure out what the value of e is equal to. Okay, given this table, I'm going to give you values of n. I want you to evaluate when n equals 1, when n equals 2, when n equals 5, and then we're going to jump to 10, 100, 1,000, and then we're going to do 10,000. So I want you to have an idea of what's going on at these particular n values. So plug these into your equation over here to this function, and let's get the values for this part of the table. Okay, if we evaluate n at 1, let me just go through one of these with you. So that would be 1 divided by 1 is 1. 1 plus 1 is, that means this entire thing is 2. Raised to the first power is 2. And basically I just did all these values, plugged them into this function, and this is our result. Now we'd like to say, as n approaches infinity, the function 1 plus 1 over n to the nth power approaches what value? Okay, so what I'm saying is n gets bigger and bigger and bigger and bigger, meaning infinity. What keeps happening? What's this keep getting closer and closer and closer to? We can round this and say 2.72 approximately. Meaning if I keep getting larger and larger, it's just going to keep getting closer and closer to this. It would just keep extending out to more and more decimal places. Okay, so f of x is equal of e to the x is now what we're going to introduce to you next, which is our natural exponential function. Okay, so that when you plug in e in your calculator, e to the first power, it's going to be approximately this value. And that's why. This concept right here is the reason why. So the very first thing we're going to do is say, let's check if you're comfortable using the value e in the calculator. So use your calculator, go to e and plug in e to the 2.1. Round your answer to 3 decimal places and let me know what you get. Okay, raise it to 3 decimal places, I get 8.166. Good. So just make sure you're able to get this value in your calculator. We're not going to spend a lot of time on that. The next thing we're going to look at is, what does the graph of this function look like? Good. So first of all, if we had we let x equal 0. When x is 0, it's 1. So that's the order pair right here, 0, 1. And then when we let x equal 1, we get e to the first power, which is that roughly 2.72 on here. It's these are really hard to scale. And then it's just going to keep increasing exponentially. So this is a rough sketch of your parent graph of e to the x. The next is we're going to use compound interest formulas for n compoundings per year and then for continuous compounding. So I'm going to pause it and write formulas for these. Okay, when we're given n times per year, we need to use this particular formula, where A represents your account balance, P is the principal, R is the rate. Don't forget your rate is always in decimals. N is times per year. And T is time. First of all, times per year, if it was biannually, what would that be? N is um N is going to be 2. What about quarterly? Or not biannually, semi-annually is 1. Biannually would also be considered, but semi-annually is the word for that. So N equals 2, and then annually would be N equals once a year. What about compounded quarterly? It would be 4 times per year. Good. So this value changes depending on how often it tells you to compute the value. And then continuous. Continuous is the one a lot of people say PERT. Okay, and it's going to be this particular formula. Alright, so let's see an example. It says use the compound interest formula, either of these, to solve A, B, and C. So first of all, it tells us our investment is $10,000 for 5 years at an interest rate of 5.55%. Now, how will we write that as a decimal? 0.055. Remember, you write rates as a decimal. Here, our T is equal to 5 years. And the money is computed semi-annually. What does semi-annual mean? That N is going to be 2. Good. So let's use, which formula will we use for this first one for part A? We will use this first one because it gave us a certain amount of times it was computed. And then the second one, it tells us quarterly. For the third one is continuous. This continuous one, you want to make sure you use this one for continuous. So let's just start with part A and use this formula, plug in all your given information, and plug this in. So the principal is going to be 10,000. 1 plus our rate, which is here, we already wrote it as a decimal, so 0.55. N, we said, was semi-annually, so it's twice. N again, and then our time was 5. Now, most people actually do fairly well with this, but the place they make the mistake is plugging it in the calculator, because the calculator doesn't do order of operations for you. So some people are successful doing the entire thing all at one time in the calculator, but they have to be very, very precise with many parentheses and many grouping things. I personally, over time, have just found that most people tend to do better if they plug this in the calculator, 0.055, divide by 2, hit enter, add 1 to that, hit enter, then raise it to the 10th power, hit enter, and then last multiply it by this. Okay, you do whatever works for you. If you're able to successfully plug the entire thing in using the appropriate amount of parentheses, good for you. If not, then I would suggest doing it the second way that I mentioned it. And so when we plug that in, we should get the value of this, 13,117. Okay, next we want to, for part B, we want to compound this thing quarterly. So remind me what that means for our N. 4 times per year. Good, so quarterly. So you basically plug in the same information, but this time let N equals 4. Okay, calculator, the second way is I would say 0.055 divided by 4, enter, plus 1, enter, raise to the 20th power, enter, times 10,000, and we should get this value for our, which we can see it's slightly different than part A when it's compounded twice a year versus compounded 4 times a year. Now let's compare that to if it's continuously compounded over and over and over again. So for continuous, we know we're using A equals P E to the RT. So we plug that in, our principal. E is our value E, the rate is still 0.055 for the same problem, and the time is still 5. Now the calculator for this is E raised to this, the multiplication of these two, then always lastly times 10,000. and we get so now you can compare if you have the same initial investment, the same amount of years, the same rate, but depending on when and how often the bank compounds, you could see the effect of that total value at the end. hmm You plug that in the calculator similarly. Make sure you can test these in your calculator and you're getting these same values so that you know you're computing the calculations correctly.